So let's say we had this satellite here, and the purpose of the satellite is to track some moving object in the air. So as this object moves, the satellite will continue to rotate so that it is always pointing at where the object is at that instant. Some quantities of interest here might be how fast does the satellite have to rotate? That may be important in choosing what motor we want to drive this satellite. So how fast this thing is rotating, well, mathematically that is theta dot, which is just what is my angular speed? The angular distance I travel over how much time it takes me to travel. That instantaneous rate of change. So what we're really doing here is we're entering the polar coordinate system. And we're not measuring the travel of an object with x and y coordinates, but instead r and theta, in which r is going to be the length of these lines. So as you can see, as this particle travels here, r is decreasing, and then it starts to increase again. And also we're tracking this thing with theta. And theta is an angle, and usually that angle is measured from the positive x-axis. So as we can see, as this particle travels, our angle is getting bigger. So at each point, our particle will have an r and theta value. A position, but in terms of r and theta. Now, when we dealt with x and y, we could describe the velocity in terms of x and y. And it was basically the change in x with time. This would be basically the x component of the velocity, I hat, and the y component of the velocity, how fast y is changing at that instant, j hat. Now, we're going to do the same thing with this polar coordinate system, but of course, we won't have this. We're going to have some new stuff in terms of r and theta. So let's talk about how an object can have a velocity vector, but in terms of r and theta. So, here's how we're going to go through this. There's two ways a particle can change. By changing its r or changing its theta. Let's just talk about changing its theta for the moment. Let's just imagine that we have a particle moving on a perfect circle. Of course, because we have a perfect circle, r is not changing. So this is going to allow us to really focus on theta. Let's say my particle is here, and then it's here. I can draw these two lines, and this right here is basically the angular distance, my angular displacement, that I traveled during some time interval. Well, we can use an equation to analyze this, and it's a very important equation, and I've seen it a lot in engineering classes. The arc length, that distance that particle traveled, is equal to the radius times the angular distance, that angle there. So if I know my radius and I know my angle, I can calculate what is the distance this particle traveled. And here's the thing, this equation works even if we shrink down to the differential level, the infinitesimal level. We move a very, very tiny angle, d theta, and as a result, we're going to move a very, very tiny distance, ds. So this equation here still applies. ds is equal to some r value, not a dr, this is obviously some big r value, times the tiny angle that we're traveling on to. if I divide this by the tiny time interval that it takes us to travel from here to there, what we get here is my velocity, my speed. So I get the speed is equal to r, and this is my angular speed, theta dot. So what we're learning here is that we can have speed just by changing our angle theta. And the speed due to this change in theta is equal to r times the angular speed, theta dot. Now, of course, we can have some sort of speed due to the changing of r. And let's say that theta can't change. So let's imagine that. So here's our origin, and let's say our particle is moving this way. And as we can see, the angle of this particle does not change. It's always on the same angular line. Maybe that might be 45 degrees. What is changing, though, is our r. Our r starts small, but it gets bigger and bigger. So the speed here is simply how much is my r changing with respect to time. And this really is the speed due to the changing of r, Vr. And let me say over here, this is v theta, the speed due to the changing of the angle of this particle. And of course, dr dt is also known as r dot. So let's go back to this example, and our particle is traveling leftwards. Of course, it's more than possible to have both of these things going on. If our particle is here, say, and of course here's my r, I'm definitely going to have speed due to the change in angle, because as this red particle travels, the angle is definitely changing. So I definitely will have this tangential speed here, this r theta dot. And remember, I'm drawing this speed tangential 90 degrees like this because I'm imagining that we have that tiny s is equal to r theta equation, and here is my tiny little distance that I'm traveling. Yeah, so this part, this component of speed is perpendicular to my radius at this instant. Also, as we can see, we'll have this part, we'll have the speed due to the changing of the radius. If we zoom in here, we can definitely tell that my radius is changing at this instant. It's increasing, actually. So because of that, we're going to have the speed from the changing of our r coordinate. And this gives us speed outwards from our radial line, our radius. So because both of these effects, both of these things are happening at the same time, our particle has both of these characteristics, what we have to do is we have to add them together so we can see the true speed, the true velocity. And of course, since these things are vectors, since they're directed in specific directions, I have to do that whole tip to tail vector adding here to get the true velocity vector, which of course is always going to be tangent to my path. So if I calculated this number and it was like a 2, and I calculated this number and it was a 3, I would have to do Pythagorean theorem to figure out the length of my hypotenuse, which of course is my speed, the magnitude of my velocity vector. and that would be radical 13 meters per second. So we have this transverse component of my true velocity, which is the part of the velocity due to the changing of the angle, and it's always directed perpendicular to r, as we can see here. And we have the radial component of velocity, the part of the velocity due to the changing of the radius, and it's directed outwards from a particle in the direction of increasing r. So we have a nice vector equation we can write to describe all this. The true velocity will equal that transverse component, which is going to be in the transverse direction. I'll talk about that in a second. Added with the radial velocity, which is in the radial direction. So these are just like I and j. It's just like x and y. Just like we have to say x is this way or y is this way, or maybe we're tilting it for a ramp problem. X is this way, y is this way. Same thing here. What I have is the theta direction, that transverse direction, and that will be in the direction of increasing theta. So my theta is increasing because we're based off that x-axis. So here's a small theta, here's a bigger theta. This is the direction of increasing angle, so therefore this is my transverse axis, you might say. And here is my radial axis, which is outwards in the direction of increasing r. So my radial component is in that radial axis, and my transverse component velocity is in the transverse axis, just like the x and y components of velocity are in the x and the y directions. Same thing. So, just to try this out, let's say I was here. My radial line would be this, so this would be my r. My theta would be this right here, of course. My r-axis will be away from my origin in the direction of increasing r. My theta axis, my transverse axis, would still be this way because this is that general direction of increasing angle. And of course it also has to be perpendicular to r. As we can see, my true velocity is always tangent to my path in blue. So this is going to be my true velocity vector, at least the direction of it. And as we can see, my transverse component will be a positive, and my radial component would have to be in the negative radial direction. So this number would have to be negative. In other words, theta dot would have to be negative, which makes sense because as time goes on, my radius, that change in r, my change in radius is negative because my radius is decreasing. So here is velocity in terms of polar coordinates. We can have velocity from our transverse component, which is due to the changing of our angle, and is equal to r times our angular speed, theta dot. And we can have velocity due to the radial component, which is due to the changing of our radius of the particle. So of course, we can have this entire conversation for acceleration as well. Now for acceleration, like velocity, we will be able to split it up into a transverse part and a radial part, but the equations for each one of these are not as simple as for velocity. So yeah, here are the equations we use to calculate our transverse and radial components of acceleration. Definitely not as easy as r theta dot and r dot. But the logic is the same. If my particle is here at the moment, my r-axis will be radially outwards. My theta axis will be perpendicular to that r. And for whatever reason, let's say we knew that our acceleration was this way. And it's kind of annoying because we can look at a path, at an object moving, and we can know where its velocity vector is, but acceleration is not as intuitive. But if our acceleration was in this direction, we would have a negative r component of acceleration and a positive transverse component of acceleration. It's still similar to our thought process with the velocity in that respect. We have our r component and our theta component of acceleration. It's just these components are described with more difficult equations, but it's in terms of things like angular acceleration, radial acceleration, you might say, things like that. So we'll definitely want to do some practice problems to really solidify this whole thing. This is really a new whole framework. It's a whole new way of thinking. It's a new coordinate system. So in the next couple of videos, we'll go through some practice problems and really smooth this out and make sure we get it.